over assignment. Kumi wanted me to go over assignment 37, number 7, and she also requests to go over the quiz, number 12 quiz and number 13 quiz. So do you want to go over quiz 12 and 13 first before I go over assignment 37, or do
Yeah.
you want me?
Yeah. That can also for the other student.
Yes.
Thank you.
Kuma, work harder.
She
Harder,
is
harder
trying.
than this. I will.
Okay. So you want me to go ahead and do assignment 37, or?
No, quiz first.
Oh, okay. Do you want to go? You want to go ahead and go over the quiz 12 and 13, or do you want me to go over it?
Yeah, 12 and 13. Whatever they ask for.
Okay. All right. So I'm going to go ahead and go to share my screen. Okay. So share screen. Let me see. Going to be sharing this one. Share. Okay. All right. So we'll go into. So this is 14. So this is. Let me see. 14. This is 11, and this is 12. Okay, maximize it. Okay, can you see that? Okay. Can everyone see this? Okay. Can you see my screen?
Yeah.
Yeah, that's 12,
Yes, Sam.
right, Sam?
Yeah, this is quiz 12.
Okay, we can see 1, 2, and 3.
Okay, yeah, that should be the one that, yes. So this is so this one said to find the critical frequency of low pass filter is increased. The bandwidth it's going to be increased because if you increase on the upper side of that of the low pass filter, so this one is increased, therefore, and you keep this one the way it is. Therefore, if this one increased, this is going. So if this one increased, therefore this one increased. So the answer would be A. Okay. And then on the number 2, if the critical frequency of a high pass filter is increased, the bandwidth it's going to be decreased because then you're going to be increased on the lower side of the frequency here. And so therefore your bandwidth can go it will go down. Okay, and then number 3, if the Q of the band pass filter is increased, the bandwidth will. Okay, that is, so you have the formula. The formula is that Q equals to F center divided by your bandwidth. And so you rearrange that. So you bring the bandwidth in front and the Q put under the BW. So therefore you got BW equal FC divided by Q. So they said if the Q is increased, so if you increase the Q, so therefore so this one is going to be operate in inverse proportional. So if this one increased, the bandwidth had to be decreases. So the answer for 3 must be B. Okay. So you follow, or do you have any question on any one of them?
Good.
Okay, you follow?
Yes. Thank you.
Okay, very good. Okay, so next one, number 4. Okay, number 4, they said the term pole in the filter terminology refer to, it's the combination, it's an RC circuit combination. That was from the handout. So this is, so if you want a single pole, it's only have a single RC circuit. Okay. That was from the handout. Okay. All right, number 5, a single resistor and a single capacitor can be connected to form a filter with a roll-off of, okay, this one you can find it, you can Google this information, but the answer it can go minus 20 dB per decade or minus 6 dB per octave. Okay, so these two combination is correct. Now, if you go, but this one is for a single RC resistor and capacitor. So you can interpret both way. It could be in the 20 dB per decade or minus 6 dB per octave. For negative 40 dB, that had to be 2 resistor and 2 capacitor. Okay, so that would be the 2 pole. 2 pole would be B, but this one they only ask for the single. So therefore, A and C is correct. So the answer would be D. Answer A and C is correct. Okay. So number 6, a bandpass response has 2 critical frequency. Remember the bandwidth is equal to upper frequency and the lower frequency, and then the center would be your center frequency. So you have 2 critical. So you got lower, you got upper and the lower. Okay. So you have any question? Anybody have questions? To give thumbs up or we're good?
I don't feel like I have a question. I feel like I just really need to sit down and figure out the single resistor and single capacitor thing.
Okay. Yeah, that is from the handout. I have to go back and look at which handout it is. I didn't put additional notes on here. So, okay, so. Okay, so that's that. Okay, so this is number 7. Okay, the number 7, the lowest frequency passed by a low pass filter is, okay, a low pass filter, it goes from 0 all the way to the cutoff, which is at the 3 dB. So therefore it could be 0 hertz is the lowest and up to the 3 dB point. So whatever the frequency at that point. So the answer is B for 7. Number 8. The quality factor Q of the bandpass filter depend on the center frequency and the bandwidth, okay? Because Q is equal to F center divided by the bandwidth. Okay, so let me go ahead and push that a little bit more. Okay, so that's a little bit clearer. Okay, so that's what it is. So it depends on the center frequency and depend on the bandwidth. So center frequency and the bandwidth. So that's C for that, for question 8. Question 9, the number of poles in the filter affect the mainly the roll off, like a roll off, mainly affect the roll off. Okay. Okay, so everyone's good here. Like I said, if you have only a one combination of resistor and capacitor, that would be a 1 pole, and it's going, the roll off is going to be steep. But the one with the 2 combination, the 2 pole, which is 2 resistor, 2 capacitor, it will be roll off quicker. That's steeper, and then the third one would be even more steep until it get to the point of the ideal filter. Okay.
So the roll-off rate is greater than the greater number of resistors and capacitors.
You got it. Okay, so you have any question? Good. Okay, next one. Okay, when filters are cascaded, the roll-off rate increases. In other words, it's going to be steeper and steeper until the point that, so we're going to get pretty much steeper. So you have so you got this here. So you're going to go have something like this, roll off, and then you got the next one over, and it's going to be more steep. It's more steep until the point that we have like a cutoff. This is more of an ideal, the square here. So this is going to be roll off. So this is like a single pole. This is the next one is a 2 pole, and the next one is a 3 pole. Okay. So it's going to be, so they increase, so they will increase that. So that's 10A. 11, when the gain of the filter is minimum at the center frequency, it is called, that would be, it's a band stop, and it's a notch filter. Okay. So what they're saying is something similar to this. So you have a frequency, and it's going to be, you have is something like this. Okay. So they want at the minimum, which is here. So this is represent a notch filter or a band stop filter. So the answer is D for that one. So the answer, so B and C is correct. So number 12, identify each type of filter response: low pass, high pass, band pass, or band stop. Okay, so you look at this one here. Let me see. Okay, so this one right here, this will look like, so this is represent a band pass. You have a maximum at the center frequency right here. Okay, so this is represent a band pass. So C is 12. So anybody having question? You good? Okay.
So far we got an A.
Good, good.
All right. So the next one. Okay. So question 13, identify each type of filter. So what is this one?
Low pass.
Okay.
Got filter.
Okay, you got it. Okay. So what is this one right here? Number 14.
Band stop.
Okay, you got it, because that's represent band stop, or that's what you call a notch filter. So that's two, they have two names. This one is called a band stop as well as a notch filter. Okay. Some people prefer using notch filter, some prefer band stop filter. Okay. All right. Any question?
No.
Good. Okay. Next one. Okay, identify each type of filter. Okay, what is this one?
I pass.
You got it. Okay, so B is for 15. Okay, number 16, what determines selectivity in a band pass filter? Okay. So yeah, that is a band pass filter. It's come into that Q minute ago that that I did earlier. This one right here, Q equals the bandwidth divided by the center frequency. So mainly is the selectivity is depend on the Q. Q is what they call selectivity. Okay. So this one here, all right. So number, let me see, number 17. Oops. 17. Okay, so 17. Let me see, shrink it down. Okay, so 17, you can't see B, but the answer is A. So which one would be have more? Which one would have a narrow bandwidth? The higher the Q, the lower the bandwidth. Okay, so like here, the higher the bandwidth, the higher the Q, the lower the bandwidth. Okay.
Yeah, you can just plug them into the formula and see how it turns out.
Yes, exactly. Okay. All right. So anybody have question on quiz number 12?
You got an A, Q-Me.
Now.
Okay. So everybody understand? So everyone follow this?
Excellent job.
Yes.
Sam.
Thank you. Okay. Number 4. Okay. Now we go to number 13. Okay. So 13. Did I have 13 or did I have 14? Okay. So 13. Let me see. That's 12. Did I have prepared 13? Okay. That's 12. 12. And this one is, okay, 13. Okay, 13. So determine voltage VRD for the circuit shown. Okay, so this is the formula that VRD equals ID times RD. Okay, and we know that ID is the 5 milliamps. So 5 milliamps times 1 kilo ohm. So that's come in. So your result would be 5 volt. So the answer would be A for number 1. Okay, for number 2, determine voltage Vs for the circuit shown. Okay, so Vs is right here. And then when Vs, we can use the current from ID that from here. And we just have to do it, just multiply against the resistance So I converted to kilo ohm. So and then multiply by the 5 milliamps, that will give you 1.1 volt. Okay, so the answer is C for number 2. Okay, so number 3, determine the voltage VGS for the circuit shown. Okay, so VGS, so it's going to be VG, VGS is equal VG minus VS. We know that VG is 0 volt, so that's why you got 0 volt here. And then VS, we calculated on number 2 here is 1.1 volt. So the answer is negative 1.1 volt. Okay. So the answer for 3 is A. So anybody have any question?
Nope.
Kumi, you
Nope.
good?
Nope.
Okay. All
Good.
right. Next one. Okay.
Take a picture, Kumi.
Secret.
Okay, so this one is just asking you. So this is from the handout, and so you can that is from the handout. So you just say if the drain current of the circuit shown is increased, VDS will, that would be causing to decrease. Okay. So if you look at the curve of the drain current, so you look at it when the drain, so your VDS keep on, so your VDS keep on decrease. So your drain would increase, your VDS would, so your VDS would decrease and your current would increase. So it's in reverse. And the circuit shown, so they want to know what is this circuit here? Is it a fixed bias, voltage divider, sub bias, or none of the above? Okay, so this one is pretty much a sub bias because you only have power supply at the drain that powering this whole thing and that make all this whole circuit work. Okay, so when you only have one power supply that goes into the drain, then it's only a sub bias. Okay, so the answer is C. Okay, for number 6, okay, so IDSS is equal to 20 milliamps, VGS is equal to negative 6 volt for a particular JFET. What is ID when VGS is equal to 0 volt? Okay, so that is coming to just plug in the formula that Mr. Pham from the handout. So ID is equal IDSS times the quantity 1 minus VGS divided by VGS off square. Okay, and then you just substitute in that value. So 20 milliamps, and then 1 minus the 0 volt divided by your VGS, then negative 6. So that's give you about 20 milliamps. So the answer is A on number 6.
Hey, Sam,
Yes.
on number 4, there's a little subtlety there that so when you increase the drain current, the VDS doesn't always decrease. It only decreases if RD is greater than RS.
Correct.
Because if you increase ID, VD decreases and VS increases. But since RS is smaller than RD, it increases slower than VD decreases. So you have to take into account the values of the two resistors.
Okay, yeah.
If they were the same value, then VDS would not change with IDS.
Yes, you're right. Thank you. Okay. All right, so we're number 6. Okay, we're on 7. So number 7, the same thing. We're going to plug in that value in. So this one is, we're going to apply the same thing. So they said the VGS equal VS off. So therefore negative 6 here divided by negative 6. So that would be a 1. So this one here going to be 1. So 1 minus 1 would be 0. 0 square would be still be 0. So 0 times 20, it would be 0. So that's why we have the answer 7 is B. Okay, anybody have question?
Sam,
Yes, sir.
Can we go back to question 4?
Okay.
Now, the way I got it is VDS is equal to VD minus VS, right?
Yes.
which is equal to ID, which is common to both,
Mm-hmm.
times the resistor of RD minus RS.
Mm-hmm. VD. Okay, so VDS is equal to, oops, let me go ahead and change this into something. Okay. And you said VD minus VS. Okay, so therefore, like you said, since both of them has ID as the current, so there's going to be, so this is going to be RD minus RS.
Right. So therefore, if ID is increasing,
Mm-hmm. So ID is increasing.
the resistors are all constant.
Mm-hmm.
Doesn't VDS go up?
I think that what Richard was saying about the resistant combination here.
Right.
So yeah, I have to go take a look this a little bit more onto this one here, and so right now we just go ahead and go with B. I need to look into this one, question number
Ask Mr.
4.
Pham real quick. What is he looking at this?
You have to look into the picture sharing between ID, VD8, and VG8.
Okay. So that is going to be yeah. I
We're
have
talking
to
about a graph. So what graph were you talking about that shows?
That's what I'm talking about.
Right.
VG8, ID, and VDS.
Okay.
That means you get a VGS equal -1, -2, -3, -4 somehow.
Mm-hmm.
Then you
That
can
was
see you can find the problem.
okay. So that was from the handout.
Yeah, to the handout for JFET.
JFET. JFET. Okay, so JFET.
JFET handout is right there. Where it said April 5th. There you go.
Now
That's the amplifier.
that amplifier.
You was there, Sam. You just clicked on the wrong one.
Okay, so we're looking at that. Okay.
Down.
Down, 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 down. Stop. There we go.
Thank you. Teamwork. Awesome. Okay. So we're going to go into here where you got next one. This one here.
Now next one. You can go next one. That's okay.
Okay, so next one. This one here.
Now still another one.
Okay. This one.
No, it have to be up, not going down, going up. Yeah,
Yes.
that one.
Okay.
Yes, as current go up in the ohmic region, we go up with it.
So now, if you go into the VGS -2, okay?
VGS mic 2 right here.
So right up there, you can get any point on that point. Then the VGS can be changing, right?
Yes.
However, when the ID go increase, that means maximum ID at that.
VGS is 0.
Right, so the VDS will be going back to VP. Picking up,
Pinch off right here. Yes.
yeah, that is stuck at the maximum.
Right.
So the question looked like they said, when you increase the ID, right?
Yes.
VDS will be decrease or increase. Okay. So, from the textbook, they said that will be decreased.
Right.
Still don't
Can
quite-
Can I explain something? When you increase ID, and then for increasing ID, VD should decrease. And also here, ID and IS are equal. And for increasing IS, you should increase VS. So VD decrease, VS increase. So VGS decrease. Yeah, that's what I think about that. VDS decrease.
So it depends on the values of the resistor. I can prove that.
Okay. Yeah, wait until Mr. Pham can get back. I'll explain a little bit more so he can do it. It's on his iPad. He can draw it out. Okay, so let me see. So that was 6 and 7. So everybody's okay on 5, 6, and 7.
So 4 is a question mark.
Okay, 4 is still a question mark there. Like Mr. Pham said, that was from the book, and so the answer was supposed to be decreasing. Okay, so numbers 18. So next one, number 8. Okay. So determine the value of VGSQ for the circuit shown. Okay. So you apply this here. So VGSQ equal VG minus VS. And we know that VG is -2 here. And that's at the that's going to come at the gate. And the S if we at the 0 because that's connected to common. So that's why we got -2 volt. Okay. So the answer is B for 8. Okay. Number 9, determine value of IDQ for the circuit shown. Okay. And that just apply the formula. That's IDS equal to quantity 1 minus VGS divided by VGS off quantity square. Okay. And then we just substitute in the value of the value in. So we got the IDS is 10 milliamps. So 10 milliamps here times the quantity 1 minus, so -2 at VGS divided by -8 VGS off. Okay, and square that, and you want to multiply that, comes out to 5.625 milliamp, or round it up to 5.3. So the answer is C. So anybody have question on that one? These two?
No.
Everybody's good. Okay. Next one. Okay, so number 10, determine value of VD for the circuit shown. Okay. This is just apply the formula. So VD equal VDD minus IDQ times RD. Okay. So in this case, so that was the IDQ. That was from previous step IDQ, which is right here, 5.6 or 5.63, and you substitute into here. Okay, and multiply it by the 2K. That is the resistance at the drain. Okay, and once you multiply that out, so the answer comes into about 4.75 volt. Okay. So the answer is B for B is correct answer for 10. Okay, you follow? Everybody follow?
Okay.
Okay.
It is 4.74, so therefore we got a question mark.
Yeah, 7.4. That's close enough.
Now I'm
So
just teasing you, man.
Depending on whether you round off the number here.
I
and
know,
so
I
that-
know, I know.
It's all
I'm just
dependent on
teasing
that.
you.
Yeah, so
Question
that's close enough. That's close enough. 7 is way beyond, and 5 is way beyond, and so 4 is close enough. Okay.
Yep, you're right.
All right, number 11, determine a value of VDS for the circuit shown, okay? So now we just apply the formula. So here's VD, and so VDS equal VD minus VS. So We know that from number 10, it's 4.75 voltage for VD minus the 0 volt for the source, because it's connected to the common. So that comes into 4.75 volt. So the answer is C for 11.
VD equals VS.
Yes, you got it. No, VD.
No, VD equals VDS.
Yes, okay, you got it. Okay. So this is JFET is cut off. The depletion layers are pretty much touching each other, because then you got a whole bunch of. So pretty much it's touching and completely touched. Okay, look like all right. So next one. So anybody have question on 10, 11, or 12? No, okay. So next one. Okay. 13, given that the VD in the circuit shown is 5 volts, solve for ID. Okay. And I just applying the formula. So VDD minus VD divided by RD. So we got VDD is 9 volt and VD is the 5 volt, and that's divided by 4.7K, the drain resistance. So you got 0.85 milliamp. So the answer is B for 13. Okay. And 14, given that the VD in the circuit shown is 5 volt, solve for VG. Okay. So now we solve for VG. So VG equal to VDD. Okay, this is representative voltage divider right here. So VDD times R2 divided by the quantity R1 plus R2. Okay, and once you solve that, the answers come to 1.62 volt. So the answer is A for 14. Okay, number 15, given that VDD in the circuit shown is 5 volts, solve for VS, okay? So VS is equal to ID times RS. So ID we got was 0.85 milliamps times RS, 3.3 kilo ohm, which equal to, and the result is 2.81 volt. Okay, so the answer is C for 15. Any question? No, okay, very good. Next one. Okay, 16, the pinch-off voltage has the same magnitude as the VGS, yeah, VGS off, because it just, the VP would be then, it would be the same magnitude, but it would not be the negative value. Remember, the VGS would be positive, negative, and the pinch-off would be positive. So that's one I said, VP is absolute value of VGS off. And so that's why we got a positive. So and it's going to be the gate source cutoff voltage. Okay. So the answer is D for that one. Okay, number 7, transconductance indicates is how effectively the input voltage control the, okay, so mainly control the input resistance. Okay, so mainly have to do with what that curve that Mr. Pham was alluded to earlier.
I got a question on 16 real quick.
Okay.
So it seemed like in the handout, he was emphasizing that the pinch off in the V, one or the other will be in the data sheet, but never
Yes.
both. Is that just because you're just already assuming that it's the opposite?
Yeah, because that's how it works. The pinch off is always the opposite of VGS off.
Okay,
Yes. So they can give you one or the other. They can
That's
use
all you
VP.
need.
Yes, that's all you need.
They're the same magnitude, but have the different sign.
Yes,
Right.
that's yes.
thank you, Mr. Smith.
Right. Okay, so number 18, a JFET has IDSS equal 20 milliamps and VP equal 3 volt. What is the drain current at VP equals 5 volt? Okay, so Yeah, so your IDSS is 20 milliamps, your V pinch off is at 3 volt, and so VGS off is equal to negative of VP, so therefore it's going to be at negative 3 volt, okay? So when you're applying the positive 5 volt at the pinch off, therefore the VGS is going to be at the negative 5, but this one is cut off at already at negative 3 volt, so therefore you're not going to get any current at all. It's going to be okay, so this one is only operate up to the negative 3 volt. Okay. Negative 3 volt. So here you got the pinch off at positive 5. So therefore, if you look at the opposite of this would be negative 5 volt. So therefore, it's out of range. It's out of this range. Okay, so therefore, there's no current flow. Okay, so that's the assignment number. So that's quiz number 13.
Sam, before we leave that, I went back to number 4 and I checked my algebra and I made a mistake with a negative sign. So the answer is right, that when you increase in that circuit, when you increase ID,
Yes,
the VDS always goes down.
yes.
Understood.
Can you I didn't hear everything he said. What
Yeah,
did he
I
say
couldn't hear,
again?
I couldn't hear Richard.
Hey, Richard, can you repeat that?
He sounds muted or something.
Yeah,
Let me check my audio setting.
Yeah, check your microphone.
It's
It
your
doesn't-
bass. You just got really poor bass microphone.
He's in the bathroom. No.
I'm using earbuds. Is that better?
It's very horrible bass.
Can you take your mask off?
Yeah, we need to hear from
There's
you,
a-
Richard. We need to hear from you, Richard.
Let me share my screen. I can just show you the.
Yeah,
Okay,
that's a good
okay, let's
idea.
go
Let
ahead
me
and
share
stop.
screen.
Okay, go ahead and share your screen, Richard.
I think he's in a wooden room.
It's insulated.
Okay, can you see this here in the mirror?
Yeah,
Right,
I
right.
can see it. Yes.
Okay, so here's the equation. The drain voltage is equal to VDD minus RDID.
Yeah.
Source voltage is equal to RS times ID.
Okay.
VDS is equal to VD minus VS. And so if you substitute in that for VD and VS, you get VDS equals this quantity, which is VD, and this quantity, which is VS. Then if you do the algebra and you take out the common ID from the equation, you get VDS is equal to VD minus ID times the sum of RD and RS. So if ID goes up, VS goes, this column goes up and VDS goes down.
Yes. Okay. Thank you. That's clear. So we're looking at that formula. It make it really, really clear. Thank
So
you.
what are we saying the answer is to number 4?
Decrease.
The answer is B, decreasing.
Okay.
Yeah.
Thank you, Richard.
You said the answer is B, Sam?
B as in boy.
Okay, thank you.
Okay, so that's quiz number 12 and 13. Okay. So we still have a few people that still haven't finished test taking quiz 14 yet. Do you, Mr. Pham, do you want me to go over quiz 14?
14, that means last week, right?
Yes, sir.
Monday. Okay. go
Okay.
ahead.
Okay. Well, you want me to go over this one on Monday or next week or?
Now.
You want to go now? Okay. All right. So now we go over. Okay. So we're gonna go over that number assignment. Okay. Okay, so given so question number 1, a given JFET has the following characteristic: IDSS equal 12 milliamps, VGS off equals -5 volt, and GM0 is equal to 3000 or transconducted 3000 microsecond. Determine GM when VGS is equal to -2 volt, okay? And you just apply the formula like GM equal to GM0 times the quantity 1 minus VGS divided VGS off, okay? And we just substitute in those value in. So we know GM0 is going to be 3000 microseconds. So I converted to millisiemens. So therefore 3 millisiemens. Okay, so therefore now we got 1 minus the quantity -2, -2 volt, -2 volt divided by the -5 volt. Okay, so we substitute in that and do calculation. So GM comes to 1.8 millisiemens. So the answer is B for number 1. Okay, so in question 1. Okay, very good. Okay, question 2. A given JFET has the following characteristic: IDSS equal 12 milliamps, VGS off equal to -5 volt, and the transconductance equal 3000 microsiemens, and determine ID when VGS is equal to -2 volt. Okay, and we just apply the formula. So ID equal to IDSS times the quantity 1 minus VGS divided by VGS off, quantity square. And then we put in that number in. So IDS is 12 milliamps times the quantity 1 minus the -2 volt divided -5 volt. That's quantity square. So we're going to multiply that. And so the answer is 4.32 milliamps. So the answer is A for number 2. Okay, so next one. Okay, so question number 3. For p-channel JFET shown, determine VGS at Q, okay, VGSQ. Okay, so we just apply that formula. So VGSQ equal to VG minus VS, okay? So VG, we know is a +2 volt that's coming from here. So minus the 0 volt at the source, which is connected to the common. So that's why you only have 2 volt. So the answer is C for number 3. Okay. You good?
Yeah. Yeah.
Okay, very good. Okay, question 4. Okay, for the p-channel JFET shown, determine IDQ. Okay, so this one, the same thing. Apply the formula IDQ equal to IDSS times the quantity 1 minus VGS divided by VGS off, quantity square. Okay, and then we substitute in all the values. So 8 milliamps, so 8 milliamps from 8 milliamps here. So IDS 8 milliamps, 1 minus the 2 volt divided by the 8 volt, the VGS off. Okay, so VGS off is +8, quantity square. And then once you put in your calculator, and you should get a 4.5 milliamps. So the answer is A for number 4.
Good.
All right. Number 5, for p-channel JFET shown, determine VRS, okay? So VRS equals VRD, VRD is equals ID times RD, okay? So we got VD, that was from question number 5, number 4, and which is 4.5 milliamps times 1.2 kilo ohm for RD. So your answer comes to 5.4 volt. So the answer is C. Okay, for number 6, for p-channel JFET shown, determine VDS, okay? So VDS equal VD minus VS, okay? So therefore VD plus the VRD minus the 0 volt, okay? So we got this in -10 volt here, so plus the 5.4 volt minus 0, so you end up with -4.6 volt. Okay, so the answer is A for number 6. Okay, now number 7. Okay, determine the value of ID required to sub-bias a P channel with IDS 25 milliamps and VGS off equals 5 volt. VGS is to be 5 volt, okay? So we substitute in our formula. So ID Q equal IDS times the quantity 1 minus VGS divided by VGS off quantity square. So that's going to be 25 milliamps times the quantity 1 minus 5 volt divided by 15 volt quantity square. And once you put that in, do your calculation, it should become to about 11.1 milliamp. So the answer is A for number 7.
Number 6, one more time, please.
Okay, number 6, okay, so number 6. Okay. So VDS, so it's going to be, so here we know that VS is going to be 0 because it's connected to common. And so VD, okay, so minus the voltage drop over this one. So minus on minus. So therefore, so this, so we're going to be, so whatever it is had to be 5 volt here. Had to be total of negative 10 volt here. So if you that negative 4 plus the minus the 5.4, it should become to 10. So that's why you got negative 10 volt plus the 5.4 volt. The 5.4 volt is the 1 VD right here.
Okay.
And
thank you.
VDS is the negative 10 volt because that's what we have here. It's a negative 10 side. Okay,
Thank you.
you're welcome. Okay, so we're okay on 7. Number 8, determine value of RS required to sub-bias a P channel with IDS S equal 25 milliamps and VGS off equal 15 volt. VGS is to be 5 volt. Okay, so we just do the formula. So RS equals VGS divided by IDQ. Okay, so that's 5 volt divided by 11.1 milliamps. Okay, so it comes up to 450 ohm. Okay, so number 8 is B.
Okay.
All right. Okay, so next one. All right, number 9, for a certain D MOSFET. So this is the depletion MOSFET. IDSS equals 18 milliamps and VGS off equals positive 10 volt. Is this an N channel or a P channel? Okay. Okay, very good. Because your VGS is positive, so therefore it's a P channel MOSFET. Very good. Okay, for a certain D MOSFET, IDSS equal to 18 milliamps and VGS off equal positive 10 volt. Determine ID at VGS equal positive 4 volt. You have a question, Hugh?
Oh, sorry, I was I was trying to get my mic to work. Yeah.
Oh, okay.
Whenever you're done with this review, can we go over that assignment just real quick, just so I can get a better understanding? I can like share my screen and.
Okay. Let me go ahead and try to finish
just real
this.
quick.
Okay.
Yeah. Thanks.
Very good. Thank you. Okay, so so we just substitute in the formula in. So you put in the formula and just substitute in the value. So you do that and it should be coming about 6.5 milliamps. So the one that's closest is B, so 6.48 milliamps. Look like I did round it off. And so, okay, so B is the answer for number 10. Okay, for number 11, let me go and try and get this one up a little bit. Okay, for 11, for certain D MOSFET, IDSS equal to 18 milliamps and VGS off equal positive 10 volt. Determine ID at VGS equal negative 4 volt. Okay, so therefore you just have to do the same thing and just substitute in. The VGS will be negative 4. And into that, and then you do your calculation. So the answer comes to 35.28 milliamps. Okay, so B is your answer for number 11.
Good.
Okay, so everything's good there. Okay, so that's pretty much it. So anybody have any question?
Thank you.
You're welcome. Okay, let me go ahead and stop it. Let me go ahead, Hugh. We'll give you a chance to go share us your screen.
Okay, cool. Yeah. Yep. All right. Okay. So this is the assignment for the e-calculations CB amplifier.
Okay.
I guess what I was doing wrong was I wasn't declaring the formula right.
Yes.
So in the formula, I have to match it to what it's declared here.
Yes, so yes, you're going to be match it to the anything that declare up on top. So you missing is VEE. So look at your Excel. What Mr. Pham want as VEE? So go back to your Excel, click on that. So according to that, it's on line number 56 or 51. It's right there.
Oh,
line
see,
51. Yeah. So he want VEE to be negative 6. So
okay.
you want to type that double on top and. So
okay. So yes. I write that out, and then so as far as this portion, it should never be any actual value.
Yeah, because we want to change the value just one place. If we change everything in the global, then we can still run a program, and then we just have to really just change our expected value.
All right.
And rather than sitting there trying to change everything every time that you do it, you have to go in there and sort of change everything out again and again and again. We just do like 1 or 2 places, and then we can run the program.
Let me see. Double VEE equals -6. That changes everything then, I guess.
Yes.
So now, but when I do that,
okay, don't forget the semicolon at the end. It's after every statement, it has to be semicolon.
Oh, that's what okay.
Okay, now as you can see, void, see that squiggly line under that void is
okay. So this should always be reflective of the formula and then whatever variables is. Yes, okay.
You got it.
Okay, because it's so easy to like do a formula and get it to pass. So you never know if it's like really wrong until you kind of have to go over to the Excel and.
Yeah, that's why when you're working at a company, you know, they're going to send you a document just like this Excel to you, and you to do some programming and to do some testing for them, because they don't have the time for it. So they send you all this information. So you have to you know, do your coding, and then to run it to make sure everything's correct, and then before you save it and send it back to whoever it is, the engineer that requests this information.
Okay, cool. Thank you. Thank you.
You're welcome. Okay. All right. So now we go to, I think Kumi want the number assignment 37, number 7. Okay, let me go ahead.
Please, just one.
Okay, just put it quickly. Okay. All right. So let me see. Okay, so we're gonna be doing that. So 37, number 7. Okay, so number 7 should be pretty. So that's what that's what it's come directly from Mr. Pham. So it's not okay. So we're gonna be doing this. So number 37. So let me go ahead and do this split screen 37. Okay. So line 45 here. So line 45. Okay, so line 45 would be that. So he said to calculate voltage gain. Okay, so AV equal 4.6. There's no unit, and GM equal times the quantity times AC load. Okay, so therefore in number in 7 it should be straightforward. Okay. Straightforward, yeah. The formula is just GM times the R load, because GM it would be in millisiemens, and then RL R load is in kilo ohm. So kilo ohm would undo the milli. And right here, so therefore, so this is 1.1 times the 3.7. So that would be 1 with a 3.7 plus another 0.1. So that's going to be a little bit over 4. So that's
Because
why.
on my, I put gain equal GM time
Mhm.
AC load is like crazy rate.
Well,
Yeah.
depend if you didn't define what AC load. If you define here to be AC load, then you have to use that AC load in the other one.
Okay, I got it.
Yeah,
Thank
because
you.
this one, yeah, number 4 said to use all load, and so therefore, oh, okay, so that's why the
Yeah, that
formula
one.
doesn't match. Okay, so it doesn't match up. Yeah, so whatever you use in here to substitute in there, so that's all
Okay.
load. Yes, okay,
Perfect. Thank you.
welcome. Okay, all right, back to you, Mr. Pham. Thank you.
Okay, thank you, Sam. You do a very good job.
You're welcome. Thank you.
You almost take all your time, Mr. Fan.
Okay, so I need to share my screen.
Oh, Chris.
Okay, so before we go back to the JFET amplifier, I want to make sure you can understand the way we're teaching this program changing a lot. Okay, the thing I try to find the better way after the course you're able to do your technician job. And also if you go to the college or university, they will help. Okay, so this time I emphasize on the quiz. That means on the quiz, if you can do it right away, then you'll be okay. Okay, so depend on how many quizzes in the program we get, you must be doing. That's why to be complete the program from the continuing education, you have to meet two requirements. The first total hour for the program must be 900 hours. And the second thing is the work in the program you must be done. Okay, and this is a hands-on training program. You get a lecture, then you have to get the lab. However, in this time, we cannot get back to the lab. So that's why we still on the hardware. But on the other one, I want you to make sure all of the quiz should be uploaded so Sam can take it out and report to me. Okay. For the first day to do the quiz, if you upload it, then you can get grade for A or B or C or D. However, after that, no matter what, you only get C to satisfy. Okay? So today, we also get the quiz. Do the best you think you can do. Okay? Now, go back to the JFET and also you understand in the path bipolar. In a bipolar, you can get common emitter, common collector, common base. JFET, you can get a common source, common gate, and common drain. They're very similar, okay? Either bipolar JFET you want to doing on the AC, then you must be following the rules. They say set on the DC source to 0 and replace them by a short circuit. Second thing, replace on capacitor by a short circuit equivalence. Remove on elements by part by the short circuit equivalent. Okay, as introduced by step 1 and step 2. Redraw network in a more convenient and logical form. Okay, the first thing we learn, common source. Few things when you're looking into the circuitry, you can tell right away, this is a common source or common gate or common drain. Common source, the input signal applied to the gate and the output from the drain. Then you know that common source. And especially the relation between the input and the output. That means input output will be our phase. Input positive, output negative. That's the minimum thing you have to know. And if you go into more detail, then what we need to do calculation. Okay, we need to know what that means. What is the input impedance to that amplifier? What is the output impedance? Okay, and also they want to know the gain, and you're able to calculate the output if you get the input. Okay, that's a general picture. And you can answer right away if they're asking you. Okay, any question on this page? If it's not, okay, so now we go to the next one. Okay, so this is a common source. They just try to repeat it. But I want to know, you understand this is a DC coupling. Okay, that means they allow sideways to go to the gate. Any DC from the input here cannot go. That's blocked by this capacitor. And also this capacitor, the same name, AC coupling or DC blocking. The thing is on this side, the load here like the speaker. This is like your voice, okay? And the voice they go into the speaker, you don't want any DC. So that's why this capacitor here will be block any DC from the drain. You already know. At the drain here, you get two different voltage. One the DC voltage for bias. Also, you get the sideway for the signal. Okay? And the capacitor here, they will be called a bypass capacitor. Okay? That will be telling you what that means. If the any AC voltage, AC signal at the source here, the capacitor will be shorted to ground. So basically bypass what? They will be bypass RS in equal to an ohm. That means AC current cannot go through RS. That's a bypass. Okay. And now they try to separate it for you. This is the input here, and you need the RG equal 1 mega ohm here. Okay, if it not get this resistor, the sideway will be shorted to ground. So you cannot get the sideway go to the circuitry. And the output here, they can get the, you say some different textbook or some different where they're talking about output impedance, RL. R means resistance, L means load. That means the output resistance. Or normally I using Z out. That's the same thing, output resistance. Okay. In this case, they get RD and parallel with the R load. That's the thing when you try to short, okay, try to short the 15 volt. So this will be drought. And also that also be drought, okay? And RL and RD connect to the same drain and both go to the drought, so that's why they in parallel, okay? So that's why you can get RD parallel RL. Okay, now this is they draw, you see, any in the dark part in here. That means inside the JFET, you couldn't do anything. So basically from the drain, you get the current flowing into the source, and the value will be Gm times VGS. And also from the drain into the source, you get the resistance RD. Okay, that means internal resistance from the drain to the source for this JFET. And this resistance value will be very big. So that's why in normally calculation, they ignore that RD. So we don't take the account on that one. If you want, when you go into the engineering level, they design something, so they need more accurate, then they need to take account for RD. Okay, and this is the gate, and the V in will be here. Okay, then after the calculation, okay, they given to you. First thing, G in input impedance means you're looking from here into the amplifier. Okay, then you can see the big RG we already display on the other 1 mega ohm. That's the input impedance. And the output impedance, okay, depending on the drain in here, you get RD and R load or only RD. In this case, they show you that only RD, okay? Why they say almost equal RD? The thing is they say this bigger than RD. That means if you're looking at, you can say this is the resistor here for RD. And now basically output impedance, you're looking at this way. Then you can see R small d parallel R big D. But R small d too big compared to RD. Okay, so that's why they say output impedance only equal RD. Okay, we ignore R small d. And now the gain. The gain, let's see.
Mr. Pham,
Yeah,
sorry, I'm not totally understanding why that internal resistor gets ignored.
you mean
Small RD. Why does
small-
that get it?
Oh, you mean RD here?
Yeah, the internal resistor. Yes.
What happened to that resistance?
Yeah, I don't understand. Why is it get ignored?
You understand they will be a very big value.
Okay.
If you're talking about using R small d, right?
Yeah.
Who care? They can
Okay.
put anything they wanted. I don't care.
Okay.
Depend on the different textbook. If you can looking into the textbook, or you can go to the Google, okay, then see what internal resistance that simple will be using R big D, R small d, okay.
Hey, Mr.
And
Pham,
only telling you that will be, I said that's a resistance inside the JFET. We
Yeah.
cannot do anything. They build that way.
hey, Mr. Pham,
Yes, sir.
can I, you can correct me if I'm wrong. So you're saying that based on what he's asking, you're saying that R small d is so large, and it's so large, it's even so much larger than RD, that the small RD doesn't matter. In other words, little RD, the little RD that you got circled here is extreme. It's an extremely large value.
Right, that's what I said.
Okay, let me finish. It's an extremely large value. And typically, when we parallel two resistors together, the answer is usually the smaller one, correct?
The answer will be the small value.
Right. So RD is a lot smaller. Big RD is a lot smaller than little RD. So then, therefore, the little RD is insignificant. In other words, we don't need it.
Okay. I think I get it now. It's just that the resistance is so great there, it's almost insignificant.
Right. That's
Okay.
what I think. That's what I hear. It sounds to me like what
Okay.
he's saying.
Okay, I got it. That sounds right.
Okay.
Yeah, thanks.
Maybe it's a better way to think of it, the resistance are small RD is so large that the current to it is insignificant.
Yeah,
So
it can't, yeah.
all of the actual current goes to RD, and that's what determines the voltage.
Okay, yeah, that makes sense now.
Thanks
Okay,
a lot,
thanks.
Rich.
Thank you.
Okay,
Thank you.
now. Gain, AV. V out. V in. So what V in equal? That means you get a signal right here, V in here. What V in equal?
Yes.
Who can tell me what V
Yes.
in equal?
BGS?
Exactly. VGS. That means from here to the route common. That's a VGS. What V out equal?
VDS.
Okay, now you see V out. Forget this one, okay? You
Right.
get the current, okay, GM, VGS, that means the current flow. That will be value is GM, VGS. Okay? And that will be telling you V out and the current opposite direction. V out, that means from the VD to the route. That means you're counting from here to the route right here. However, the current opposite flowing from the source up. That's why you have to get the minus. Minus is telling me the input, the voltage and the current opposite direction. Okay? they will be equal minus GM VGF time. In this case will be R big D. If you not agree with that or confusing, just go ahead and ask it.
So Mr. Pham, so you're saying V out is equal to minus GM times VGS times RD?
GM VGF, right?
Right, GM,
RD.
right. You're multiplying three things there. Yeah, I got it. That's what you're doing. You're
Okay.
multiplying three things. Okay, thank you.
Now, gain AV equal V out min. Equal V out V in. V out equal minus GM VGS time RD divide V in VGS. So VGS cancel out. That's why you get finally minus GM time RD. That's just a proof for you. How come they equal minus GM time RD? Get any question? If it's not, okay, I said you can get the AV equal 25. If you do calculation, minus 25. Right? Number 25, I give it to you. But you substitute into the equation, you say AV minus 25. However, when I asking you enter value of AV, so what you think you enter? Mr. Smith, can you tell me? I given you calculation, you get AV equal minus 25. However, when I asking you, go ahead and enter the value of the gate. What value do you enter?
25. I mean, you said that when you manipulated that formula, you got, well, first of all, on the far left, you got AV equal minus 25. And I look up above and I see minus GM times RD circle. So that's why I said that. Maybe I'm confused on that part, but that's why I gave minus 25.
That's what I tell you. You calculation, you get an AV minus 25. However, I'm asking you, I want the value of the AV. What the number you enter?
25. The negatives are phase, isn't it?
Minus
You just
25.
25. Because the negative is part of that, what you got in the circle there.
It's occurring. Direction that's occurring.
No, the thing is you understand. This is the AC sideways.
Correct.
Sideways, you cannot telling it is just a negative 25 or positive 25, right? They negative, then they positive. So they are, that's what I want to make sure you understand. When you calculate the gain equal to minus, for example, minus 25, just telling you the input output will be opposite, 180 degree off phase. However, the value you want to enter, they must be the value 25, not minus 25.
Right, you in other words, what you were asking us for is the magnitude, the number itself, not the minus or plus sign.
Yeah, minus telling you.
Absolute.
Output opposite.
You mean absolute value?
Right, that absolute value. That's right. In other words, just 25. He's not concerned with the minus, because the minus just give you direction of current or whatever. Is that right, Mr. Pham? Can you?
Correct. That's
Okay.
what you will be get into the quiz today. That's why I bring it up. Otherwise, a lot of people confusing. Okay? You enter minus 25 or you enter 25. So this is the AC. You cannot say positive or negative. Only thing when you get a minus mean opposite between output and the input. Okay?
Okay.
Any question? On
Not
this
until the quiz.
part? We'll see. That will be the same thing. Okay?
Okay.
And phase relation. Common source amplifier configuration at 180 degree phase shift between input and output. Okay? So when you're doing on the lab, they display input output and they asking for the phase, the in phase, the out phase, or they can shift to the right, whatever. So this is another one. Okay, they using the fixed bias to build the amplifier. Again, I want you to make sure you understand. You get a fixed bias, cell bias from the divider bias. They can use in either type of the bias to build the amplifier. Okay? So, common source, that one you have to do it. Okay? And that one also, common source. Okay? So, I have to stop now. So we can take the test right now. But sure, you must be download.
Hey, Mr. Pham, can you go back to that screen, just the one just above? Yeah, right there.
What?
Okay, thank you.
Okay,
Thank you.
so make sure you download. Okay, quiz report from the handout. And we will run now. From now on, nobody can get into the program. The thing is, if we touch into the mouse, they screw up the timer.
Are you supposed to be seeing a fish?
I can't see anything.
You can't see the quiz.
Yeah, I forgot to say it.
Stop the timer.
Yeah, just a minute.
Mr. Pham? Mr. Pham?
Yeah,
On number 4, are you saying that VGSQ equal 1/4, and then right after that you got VGS off? What are you saying? It's 1/4 of VGS off, or what? I'm just trying to understand the question.
what VGS off? What VGS off equal?
Oh, okay, I just want to understand the question.
So you take VGS off, you
Yeah.
divide by 4.
Not, yeah, I just want to understand.
Okay.
number A was a milli VRMS or VRMS? The last one.
You just pick it up the way you think.
Okay.
You get A, B, C, D. And also you get that one, they say none of the above.
Good. Looks good,
Okay.
everyone.
So Sam, make sure
Yes.
you correct that answer.
Yes, sir.
Okay, my typo.
Okay.
Okay, so we end for today. You guys get any question on anything? What I want you guys, every quiz you're able to get through quickly. Okay? Some questions regarding to just try to see how they working. Then the answer will be quick. If we need calculation, that take a little time. So make sure everyone have to turn in your quiz, no matter take one or take two. I bet on that to given out the certificate. If you have nothing uploaded, you can stay in the program, no problem to me. But until I retire.
I retire with you, Mr. Pham.
You will be with me, right?
Yeah, I'll be here forever.
Thank you.
You're
Kumi's,
welcome.
Kumi's kids will be married and I'll still be here.
Thank you
Okay.
too.
So good night.
Good night.
Good night. Thank you, Mr. Pham.
Thank you.
Good night.